All right, so in Section 3, we're going to take a look at solving some trig equations and inequalities graphically. Right? We've done a little bit of this before with basic equations, but we're going to look at some more, like that one. That's a basic one. But then we're going to look at some more complicated ones that maybe have multiple trig functions in the same equation, and maybe a trig function to a higher power. So that's going to require us to know how do we find the period of a trig function with a higher power. Because when we write our answers, we have to put plus the period times n on the end of the answer. But that requires us to know the period. Okay, so we'll talk about how we figure that out. All right, so just kind of a reminder in general how you find all solutions to a trig equation. Okay, we've done this before. You first, if you're doing it graphically, you set your window so you're looking at one cycle. You find all the solutions in that one cycle. And then you take into account the fact that the solution is going to repeat. So you put plus the period times n. Okay, so that's what we've been doing. Okay, so in order to be able to do those two steps, a couple important things. You have to know the period of your function. Okay? If you don't know the period, you're not going to be able to set your window to one cycle. So the two formulas that we've used so far are, what's one of the formulas we've used to find period? Let's say for the sine, cosine, secant, cosecant. What's that formula? Anybody? Do you remember how we find the period of those four functions?
Isn't the period the full length of the cycle?
Yeah, and what's the formula to find it? Sure, yeah.
For radians, it's 2 pi over b.
2
and
pi
then
over
for
b.
degrees, it's 360 over b.
Or 360 over b. Yep. Now, how about the other two trig functions, the tangent and the cotangent? What's the formula to find the period of those? Yep.
Degrees is 180 over b, and radians is pi over b.
Yeah, either 180 over b in degrees or pi over b in radians. And what's b?
B is the horizontal structure shrink factor.
Yeah, it's the number that would affect the horizontal stretch or shrink. It's the coefficient of x in the argument. Yep. All right. So let's try this one. And I know we've done it algebraically, and that's what we did yesterday. But let's try it graphically, since that's more of the focus of this section. Just to remember how we do that. Okay. So if I want to solve this graphically, I'm not using inverse trig right now. What would I put in y1? Yep.
Sine x.
Okay, so let's put sine x in y1. All right. What would we put in y2? Yeah. 0.8. And now, before I graph it, I want to set my window. Let's do it in radians. Dex, what's my cycle length of the trig function in this problem?
Is it just from like pi over 2 to negative pi over 2?
No, it's a single number.
Oh, it's just one.
No, the cycle length is longer than what's the formula to find the length? Minus of the formula?
Pi over b?
That's for tangent and
Oh,
cotangent.
okay, and then it would be 2 pi over b.
2 pi over b. So what would be our cycle length in this case?
2 pi.
2 pi. Okay, so we're going to set our window from 0 to 2 pi. I didn't even check the y min and max, but I guess they're fine. Okay. So how many answers are we getting per cycle? Nick?
2.
2. Okay. How do I find the first one? Yep, and then intersect. So let's find, I'm closer to that one, so I'm going to do the one on the right first. So 2.21. And the other answer is going to be second calc, intersect again. 0.93. And those are just the answers in the first positive cycle. How do I represent all the solutions? Yep, right.
Wouldn't this be plus 2 pi?
Right, plus the period times n. And in this case, the period is 2 pi. Okay, so we've done equations like that a couple different times now. This is how we did it a little while ago. And then yesterday I showed you how to do this same thing with the ASTC chart. Okay. I think today we're gonna focus more on the graphing. Any question on that first? Okay, so just a reminder, if they ask you to find the roots or the zeros of a trig function, that means that you're setting the equation equal to 0 and solving it. You're looking for where it crosses which axis. Yep. Yeah. Okay. So just a reminder, we haven't done that in a little while, so we did a lot of that at the beginning of the year. But setting a trig function equal to 0 is how you get the roots. Okay, it's how you get the zeros. It's how you get the x-intercepts. So you might see a couple terms used interchangeably. You might see periodic function. You might also see the term periodic equation. For our purposes, they're pretty similar. Anything that's periodic means that when you graph it, it repeats. It has a cycle to it. Right? And all of the graphs that we do not only are going to have a cycle to them, but they're also going to be functions. They're all going to pass the vertical line test. Yes?
Are we going to do modular functions, modular arithmetic in this class or no?
No, we don't really get into mod. No.
Okay.
No.
That's like the only other periodic function that, besides the trig.
Yeah. All right, so now let's suppose that you graph a trig function and you find all the solutions within one cycle. Right? So let's say x1, x2, x3, xn, those are all the different intersections that you found. You have to do every one of them. So if there's 5 of them, you got to do intersect 5 times on the calculator. Once you find all the solutions in one cycle, and just kind of reminding how we do it, you put each one of those solutions down, just like we did there, and then for each one of them, put plus the period times n. N, remember, is a, what kind of number does n have to be? Yeah.
Integer.
An integer, yep. N is an integer. And because it's an integer, that means it could be a positive or a negative integer. So if n was like -2, then you would end up subtracting, which means you can get answers before the cycle you're in. Or if n is a positive integer, you get answers after the cycle you're in. Okay? But that's just the generic kind of way that we're going to write all our answers in this section. Unless they say not to write all solutions, then fine. If they just say find all the solutions in the first cycle, then no, you don't need plus the period times n because they didn't ask for all the solutions. They just said find the ones in the first cycle. Okay, so we just have to read the directions and see what it says. Okay, any question on that idea? Again, nothing new there. We've done that before. All right, so how do you find the period of a trig function that is more complex? Complex could mean you have multiple trig functions on the same side, or it could also mean you have a trig function raised to a power. So we got to kind of look at both of those things. But what we want to do in general is look at each periodic term. So if we go back to that problem I keep going ahead to, how many terms are on the left-hand side of the equal sign there? Yeah, Jeff? No, there are not two terms on the left-hand side of the equal sign. Yeah?
3.
There are 3. Yes, there are 3 terms. Can you name each term?
2 cos squared t sine t 1.
Yes. So there are 3 terms on the left-hand side. Only 2 of them are periodic. Okay, the 1, that's a constant term. So there's no period length to that. But 2 cosine squared and sine, those are periodic. So what we're going to do is find the period of each one of them. Okay, that's the first step. Once we find the period of each individual term, each individual periodic term, the period of the entire equation is the least common multiple. Okay? It's the least common multiple. So let's say it just makes something up. You had something that had a period of 2 pi, and you had another term in a problem, and it had a period of 3 pi. Well, the least common multiple of 2 pi and 3 pi would be 6 pi. Yeah, if you're not sure, just start writing out multiples. And then find one that they both have in common. That's the smallest. So if you had an equation where one term had a period of 2 pi and the other one had a period of 3 pi, the entire thing would have a cycle of 6 pi. It still doesn't explain to you how to find the period of a trig function that's raised to a power, but at least you know the concept now. Find all the periods of the periodic terms and then take the least common multiple. Okay, so let's try that here. Let's start with sine. What's the period of sine t? Yeah, 2 pi. Okay, so we know right away the period can't be less than 2 pi because the least common multiple, it can't be any smaller than the individual periods that you find. Okay, so it's at least 2 pi. Maybe it's more. Okay, now we're going to find the period of cosine squared. We haven't dealt with raising a trig function to a power yet. So a couple things. The first time we do it, we're just going to graph it and see if we can tell by looking at the picture what the period is. Eventually, we are going to come up with another formula to do. So let's put in cosine x squared. So first thing, that is how you raise a trig function to a power. You cannot type it in the way that it's written on paper. When you write something on paper, the exponent is usually in between the argument and the function. That is not how it looks on a calculator. That's how you have to do it. And you have to make sure you close that argument out because you don't want to do this. It's not the cosine of x squared. It's the cosine of x. Do that first, and then raise that result to the second power. So there is a difference. Okay, so that's how you type it in. All right, let's do set our window. Let's set it from 0 to 2 pi. And see if that gives us an idea of what the period is. And I'm going to go -2 to 2 just to zoom out a little bit. So that's a window of 0 to pi, and that's cosine squared. So we start at 0. end at 2 pi. How many cycles do you think you're looking at of cosine squared in that picture? Yeah, you're looking at 2. There's 1. There's 2. So knowing that there are 2 cycles from here to here, how long do you think one cycle of cosine to the second power is? Yep. Pi. Pi. Yep. Okay, and if you're wondering, well, if you raise it to a power like that, does it always look exactly like that kind of wave? No, it can start to kind of flatten out a little bit. So it's not always a wave. Like even this one, it looks kind of like a cosine wave. But it actually might have a little bit of a flatter spot. So the higher you make that power, the more pronounced the flatter spot gets, and that peak in the middle gets.
Oh wait, so is that how they measure like heartbeat or like that kind of monitor? Where it's just be like kind of like that kind of sine wave where it just like stays flat and then spikes and then goes back down flat. Like
Yeah, well, it is a wave kind of to it, but it's not necessarily exactly the same.
But like
repeating
when it's like the extremely flat one like that one, like it's kind of like a heartbeat monitor, like a bup.
Yeah. So that's what cosine squared looks like, and it has a cycle of pi. So what would be the least common multiple of 1 pi and 2 pi?
2 pi.
2 pi. Okay. So now that tells us a lot of things. It tells us what we need to set our window to see one full cycle, and it tells you what you need to put on the end of every answer, plus 2 pi n. That's the cycle. Okay. So that's the first step. Now let's put all of that in. So we've got 2 cosine x squared plus your sine x and plus 1. Now I want to set my window so I'm looking at exactly 1 cycle. So that would be 0 to 2 pi. 2 pi comes up a lot. It's not going to come up every time, but it does come up a lot.
It's very common.
Let's hit graph. Okay, so I'm off the screen a little bit, so I do need to zoom out so I can see it better. Let's go like -5 to 5. Okay, that's good. So because it's more complicated, it's got multiple trig functions and it's got a power, you are going to see a pattern to it, but it is not necessarily that wave we've been looking at all along. Okay. So that is 1 cycle of our graph. Going just like this. If you've set it to exactly 1 cycle, then you should be able to move this down, and it should line up exactly where that cycle ended, and the next one starts. Okay, they should line up at exactly the same point. For a continuous function like this, because this is continuous. There's no tangents in it, so there's no vertical asymptotes.
It's just so
That's what your graph looks like. So now we're trying to figure out where this graph equals 0. How many times does it look like it crosses the x-axis?
once.
Yeah, it looks like it's just once. What I would do is zoom in, just to make sure it doesn't go down and come back up and you're not seeing it. Okay, it's a pretty complicated function, so it does take a while to draw it. Okay, it doesn't look like it's dipping down under it and then coming back up. We can zoom in one more time. But I think it's just coming down and it's kind of touching it. And it looks like it's going back up.
You can also use the 0 function.
Yeah.
Yeah, you can do second calc 0.
100% sure.
So let's pick a point
Right there.
to the left, and then let's pick a point. I don't want to go Well, yeah, I'll just go like that.
You don't want to go any farther.
All right, so it looks like, all right, it's right in the middle. Because it's exactly in the middle, that pretty much confirms to me it's not dipping below. If it was a little offset to one side, then I would know it's kind of coming down and going back up, and I would have two of them kind of centered around that value. It looks like it's just one. Okay, so 4.71.
Isn't that
Yeah, yep. So it's approximately 4.71 plus 2 pi n. But that is a nice number. So if I asked you to do this as an exact answer, the way you'd want to do it is set your window from, let's go 0 to 360. Put it in degrees. Okay, you're going to see exactly the same picture because I changed. We should. Maybe I didn't change
I
something.
didn't zoom out the line.
Oh, I didn't zoom back out on the Y. That has to be negative. I think I did negative 5 to 5. Negative 5 to 5. Okay, so you're going to see exactly the same picture we had the first time because I changed the window and I changed the mode to degrees. But now I could get a nice answer if there's going to be one. Okay, if there's going to be a nice answer, you'll always be able to get it in degrees. So second calc intersect. Sorry, second calc 0.
I have to hit a cancel or clear.
Intersect won't work because we don't have another line on the graph. Okay. And when you do that, you can see you get 269.9999997. It's 270. Okay. So if you had to do it in degrees, that's how you do it. But what would you put on the end this time? Plus 360 n. And that also enables you to get the exact answer in radians because you can multiply by pi, divide by 180, and then realize it's 3 pi over 2. So that's the exact answer, 3 pi over 2 plus 2 pi. Okay. Any question on that? All right. So the only thing that was kind of annoying is we had to kind of figure out what happens when you raise something to a power that's higher than 1. So ideally, we don't want to have to graph that to figure it out every time. We want to come up with a formula. And it turns out we can use the same formulas, the 2 pi over b and the 1 pi over b. We just have to extend when you can use them to more than you're using them for now. Okay, so for any of these cases that I have on the board, sine, cosine, secant, and cosecant to an even power, or any tangent or cotangent function, even or odd. The formula that you use is pi over b. So before, you were only using the formula pi over b for tangent and cotangent. Now I'm telling you, in addition to tangent and cotangent, you can use it for all of these, sine, cosine, secant, and cosecant, if the exponent is even. For every other case you could have, it's 2 pi over b. Okay, so what are the other cases? Sine, cosine, secant, cosecant, to an odd power. And before we started raising trig functions to powers, they were always raised to the first power. So technically what we've been doing all along is raising a trig function to the first or an odd power. That's why it was 2 pi over b. Okay, not every problem is going to raise a trig function to a power. You might have some that don't. But now you know if you have something raised to a power, that is how you find the period. Okay, so any questions on when you would use 2 pi over b or pi over b? All right, so let's try a couple other problems. Let's try one that we don't have to worry about raising to a power, and then we'll do another one where we do. All right, let's try this one. So tangent x equals 3 cosine x. If we want to solve it the way we did the last one, how should we rearrange this equation first? Yeah?
I would turn tangent into cosine of x over, wait, no. Sine over cosine for tangent, or?
So if we were going to solve this algebraically, then yes, we would want to turn this into sine over cosine, and then I think it would actually end up being a quadratic type equation. In this section, we're not going to get into solving it algebraically, but yes, that is, we are going to do that eventually. I think that's in section 7.6. But for now, we're going to stick with graphing. Okay, so what would we want to do if we want to set this up so it's like that problem? Yep. Yeah, we should set it equal to 0. Okay, if we want to solve it using the root concept, we need it equal to 0. If you didn't want to solve it with roots, you could do it with intersects. Okay, we could have left it the way it was, but I'm trying to do it the same way I did the last part. Okay. What is the period of tangent? Tangent to the first power, that's tangent to an odd. Yeah? Pi. And cosine,
2 pi.
that's cosine to an odd, that's 2 pi. And the least common multiple?
2 pi.
2 pi. Okay. So that's what I need to make sure I set my window to. 0 to 2 pi. Okay, so I'm going to go back to radians. Change my window. 0 to 2 pi. I'm going to leave it on -5 to 5 because I have a tangent involved. Remember, tangent is a discontinuous function. It's got asymptotes. So it's going to go off the screen. So there's nothing I can do to keep it on the screen. All right, so we got our x min max, y min max. That looks good. Now we got to type it in. Tangent x minus 3 cosine x. Remember, we're looking for where this crosses the x-axis. How many answers does it look like we are getting per cycle? Yep. 2. Yep. And notice it ends exactly where it started. So that if you were to bend that screen around, it would connect up nicely with the other side. That's a good thing. Okay. So let's do second calc, intersect. Okay, so we've got, second calc 0. Okay, you can't do intersect. If you graph y equals 0 and then put a line right on the x-axis, then you could. All right, but I didn't do that, so I have to do it this way. Okay, so we get 2.13. It doesn't matter which one you find first, as long as you get both. Now, because the other one is on a part of the graph that is disconnected from the one we just found, you do have to be careful where you put your cursor. You've got to get it over on that part. Okay, and 1.01. Okay, go back and read the directions. So what does that mean I need to do with each of those answers? plus 2 pi n. So you can add any multiple of the period to the first two answers you found, and you could get another answer in a later or earlier cycle. And these are two distinct answers. If you add 2 pi to the top answer, you do not get the bottom one. They're totally separate answers, not repeats. Okay, questions on that? All right, let's try this one. Find all solutions to 3 sine cubed 2x minus 2 cosine x. Okay, so let's start with this one. Sine cubed. What's the formula we're going to use to find the period of sine cubed? Yeah?
Period equals 2 pi over 3.
Right, it's going to be 2 pi over, let's go back here for a second. Sine to an odd power is 2 pi over b. And in this case, b is 2. Using that number right there, 2 pi over 2. So what's the period of sine cubed 2x? Pi. Yep. So period is pi. What's the period of regular cosine?
Pi. Or sorry, 2 pi.
2 pi. What's the least common multiple, again, of 1 pi and 2 pi?
2 pi.
2 pi. Okay. So that tells me what to set my window to. We're going to go 0 to 2 pi, and we're already set for that. Now I'm going to type everything in. So you want to make sure when you type this in, you're not cubing the 3 in the front. If you do that, you're going to end up with 27. Okay, so what you want to do is put the 3, and then start a parenthesis for what you're going to cube. So sine 2x. Close the argument. And let's double check that everything looks good there. So we're cubing sine 2x. We're not cubing just the 2x because we closed the parentheses, so it'll handle order of operations okay. We put parentheses around the whole thing, so this 3 in front is not affected by that exponent. Okay, so a lot of things going on there. And then minus 2 cosine x. Okay, so we're looking for where this hits the x-axis. It was already equal to 0, so I didn't need to fix that. Now, it should end right about there, right where it started. Okay, let's take a look at that. How many times does that look like it crosses the axis?
6.
Yeah, it does. It crosses 6 times, so you do have to write them all down. But instead of doing intersect, I already have them all. So we get one at 0.5, 1.25, 1.57, 1.89, 2.65, and 4.71. Now, rather than putting plus 2 pi n on each one, I'm just going to kind of go like this. Represents adding 2 pi n to every one. Not exactly proper mathematical notation. Yeah, that's okay. Okay. So any questions on that one? Okay, that's a lot of answers. Now, I would say generally you don't have that many. But it's not harder, it just takes a little bit longer because you got to find them all.
And that one's a hard one.
So we went through the summary. Anyone need to copy anything else there? Or there? let's look at some inequalities. Solving more complicated trig inequalities is exactly the same as solving like regular inequalities. When you write your answer to an inequality, it's not going to be x equals, and then you get a single number. How do we normally write the answer to an inequality? It's written as and what? Yeah, an interval. Yep, it's written as an interval. So when we write it, we might have an interval that's a solution, and then you just have to put plus 2 pi n on each part of the interval, saying you could slide the whole interval down. So it's the same idea. So answers are going to be intervals. Keep in mind, anywhere you have a vertical asymptote, that breaks your interval. You cannot pass continuously through a vertical asymptote because it's a discontinuity. Okay. Other things we need to keep in mind, when you set your window, if you include the right edge, you don't, or if you include the left edge, you don't include the right edge. Okay, so we got to make sure we have brackets and parentheses straightened out here. The vertical asymptotes, I'm not going to make them that hard to find. Okay, if you have a vertical asymptote in a problem, it's going to be something like pi, 2 pi, or 0. It's going to be a relatively straightforward asymptote to figure out. Okay, so we'll set it up just like we were doing an equation, but then we're going to write our answer as an interval rather than a single number or multiple numbers. Right, so let's try this one. It says find all solutions, okay, where the sign is less than cotangent. All right, well, if we want to set this up like we were doing the last few problems, what would I do first? Yep. So we got a few things we have to do before we get to the using the calculator. Yeah. Okay. Yeah, it won't be equal to 0, but we're going to get it less than 0. So we're going to move the cotangent to the other side. And there's one more thing we have to do here before we try to start typing this in. What's going to happen as we try to type that in? Yeah?
Flip the sign.
Why would we want to flip the sign?
Because when subtracting, you have to flip the sign because you mentioned why, but.
So if we multiply or divide by a negative, we want to flip the sign.
Never mind.
But subtracting, we're okay. I thought you meant something else at first, but anyone else have another idea what's going to happen? Yeah?
You're going to switch from sine x minus code to sine x minus 1 divided by sine x.
So change it to sine x minus, say that again?
Tangent x.
Sine x minus tangent x?
1 divided by tangent.
Yeah, 1 divided by tangent x. So when you said flip, I thought you meant reciprocal at first, which is what we have to do. Okay, we don't have a button for cotangent, so we have to rewrite it so we can type it in. Now we're ready to type that. So we've got, clear that, we've got sine x minus 1 divided by tangent. Okay, I'm going to type it in like that, so I put the entire denominator in parentheses. All right, now before I hit graph, I need to set my window. What's the period of sine? Yep.
2 pi.
2 pi. What's the period of tangent? Yep.
Pi.
Pi. It's the same thing we've seen before. 2 pi and 1 pi. So the least common multiple of the periods is 2 pi. So let's make sure we got 0 to 2 pi as our window. Yep, looks good. And we're looking for where this graph is under the x-axis. Okay, so first, how many sections do we have to describe? That would answer the question where it's under the x-axis. How many sections, I guess, per cycle? Yep. 2. Yep. 2 sections per cycle. So let's put that there. So let's call this section 1 and section 2. Okay. Let's start to set up the parentheses and brackets and make sure we can get that right. All right. So we're going to have 2 intervals. Let's start with interval 1. Are we going to include or not include the left side of interval 1? Yep.
Not going to include it because it's an asymptote.
It's an asymptote. You cannot include the left, the low side of interval 1. So we're going to use a parenthesis. How about the end of interval 1? Right up to there. Do we include or not include the end of interval 1? Yep.
You don't include it because 0 cannot be less than 0.
Right. For that, we have to go look at the problem, and it says you have to be under the axis, not equal to it. So not include. Okay. How about interval 2? Include or not include the lower part of interval 2?
To include it?
Why?
Kind of tired right now. I don't know.
Yep.
You do not include it because it is another asymptote.
There's another asymptote there. So when we're talking about the left side of interval 2, it's going to go right up to that asymptote, but we can't include it. And how about the right end of interval 2 right there? Yeah.
We don't include it because according to the sign, it does not include where it crosses the.
Yeah, we cannot include where it crosses. It has to be under 0. Okay, so that's good. We got everything set up. We know that it's open intervals everywhere. No brackets and the whole thing. All right, now let's see what we can fill in before we even start calculating things. What is the left part of interval 1? How low does interval 1 go? Yep.
Negative infinity.
So remember, when you describe an interval, you're describing domain, not range. 0. So we go as low as 0. And we don't know how high it goes. We've got to figure that out. How about interval 2? What's the lowest that interval 2 goes? And it goes to that asymptote, but I told you I'd make the asymptote pretty easy to find. And if you know what your window is, it's right in the middle of the window. Yeah? It's pi. Yeah. You can confirm that by going to your table. Try typing in pi, and there's an asymptote there. Okay. All right. So now we've got the low part. We need to find those 2 parts that are circled. So let's do second calc 0. Okay, we got to find cursor. Okay, so I'm going to do the left part. And we get 0.90. Okay, and then on the right part, we'll do second calc 0. Okay, because it's on a different piece, we gotta get all the way over there. Okay, so let's go left, right 0, and the other one is up to but not including 5.38. Now, that's the interval in that window. But they said all solutions. So what do I need to add on each interval? Yeah?
2 pi n.
Yeah. Technically, it's like plus 2 pi n on all 4 of those, but what I usually do is just this. You can shift that interval left and right 2 pi n. And you can shift that interval left and right 2 pi n. Just understand you're shifting the whole interval. Okay. Any questions on that one? Okay, similar to an equation, you just got to think a little bit more about the brackets and parentheses when you're setting it up. Let's try this one. Right, and I want to graph it the way it is. So I don't want to get it equal to 0. I'm just going to put it in like that. What kind of term is on the left? What do we call it? I mean, it's a trig term, but there's another name for it. Yep.
Periodic
It's
term.
this is periodic. How about the term on the right? Is that periodic? No. What is that when we graph it? X squared minus 1. Yeah?
Quadratic.
Yeah, it's just a quadratic. It's going to be a parabola. So when we graph it, we have to be careful about whether or not we say our answer is going to repeat. Okay? So let's put that in. Let's just do zoom 7, just to kind of show you. So there's your periodic term. That's the wave. And there's your quadratic term. When you graph that, does the parabola repeat over and over? Does it repeat? Okay, no. Parabola doesn't repeat. So you're looking for a section of wave that is above or equal to the parabola. Okay, that would be right in there. But that section does not repeat again, because the parabola doesn't repeat again. So when you write your answer to this one, there is no plus period times n. That's what I'm getting at. Okay. Any question on why? Okay, so I'm not going to go through the intersects, but I'll show you how it would look. You can include the left end of the interval because you can equal. You can include the right end of the interval because it would be equal. And now we just have to find these two intersection points. And then we're good. Okay? And you write down the x value. So any question how you'd find the intersection points? But don't put plus 2 pi n, because it doesn't. That answer does not repeat again anywhere else. Anywhere other than that green section, the wave is under the parabola. That is the only section where it's above. That's it. All right, so the last one is a double inequality. So a double inequality, we kind of looked at that when we talked about finding domain of inverse trig functions on Monday. That's where you have the two inequalities and you have a left, a middle, and a right. So to solve a double inequality, what we're going to do is set it up so we graph all three parts. So you're going to need y1, y2, and y3. And then we interpret the result that we're looking for. All right? So whether or not the answer repeats, well, I guess it depends on your terms. Let's graph this and see what happens. When you put a number, just looking at the middle, when you put a number in front of a trig function, what kind of transformation is that? Yeah?
Vertical stretch.
Right, it's a vertical stretch. This is a variable in front of a trig function. So what's going to happen here is a variable vertical stretch. So as you get towards the origin, the wave is really small. And as you start moving away from the origin, the wave gets more and more stretched out. So it's a variable vertical stretch. Okay. Well, let's graph and see what we've got. Okay, we've got negative x. So a line with a slope of -1 going through the origin. We've got positive x, line with a slope of +1. And then I've got my variable vertical stretch, x sine x. Okay. It doesn't matter which ones you put in y1, 2, and 3. But the important thing we're looking for is, where is this wave going to be above the negatively sloped line and below the positively sloped line? So let's hit graph. There's my negatively sloped line. There's my positively sloped line. And we're zoomed in kind of far, so it's going to be hard to see. So let's zoom out. Let's go zoom 3 and just hit enter. Okay, so I want to be above that line, above the blue, and below the red. Is there any section where that wave is above the blue and below the red?
Uh, 0 to infinity.
Yeah, anywhere to the right of the y-axis, my wave is above the blue, but it's under the red. And that's what they want here. I'm just using colors to make it a little simpler. So above the blue and below the red. So that's everything greater than or equal to 0. Now, if they said, where are you under the blue and above the red, that would be everything smaller than 0. Smaller than or equal to 0. So that's a double inequality. Generally, you're kind of looking for where something is, I guess, sandwiched between two things. Any question on that? And that also shows the variable vertical stretch pretty well. The further you go from the origin, the more that the amplitude starts to increase. All right. So that's 7-3. Okay, so those will be the questions for tonight. The 19 to 25 and 33 to 37, those are odd. Okay, 29 to 31, 11 to 15, and 5, 6, 7, those are all. Again, a couple reminders. I plan on being after school tomorrow for extra help. If something happens because of weather, I will send you an email letting you know what the plan would be for Friday. So the two options for the plan for Friday would be either, depending on, I got to look at the material, would either be we just have the test on what we've learned so far, or we learn the next lesson and skip it. But I don't know that yet because I haven't looked that far ahead. But I will send you an email if there's no school tomorrow. So make sure you check your email.